Okay, I want to talk about the zeros of a polynomial and along with that synthetic division. And the way we define a zero is we say the number k is a zero of the polynomial p of x if p of k equals 0. So in other words, when I plug k into my polynomial, I get 0. Now we have some other ways of saying this. We can say that k is a root of the polynomial or a solution to the equation p of x equals 0. Or in the graphical sense, a 0 or a root shows up as an intercept, an x-intercept. So your zeros are where your polynomial cross the x-axis. Okay, now what does this have to do with division? Well, think for a moment. If k is a 0, that means p of k equals 0, right? Well, just think hypothetically, if I had something like this, p of x equals q of x times x minus k, then if in this case, if I plug in k for x, well, here I have k minus k, that becomes 0, and so I end up with 0. So if k is a 0, it makes sense that maybe we have this factor here is x minus k. And in fact, we can have a theorem that says the number k is a 0 of a polynomial if and only if x minus k is a factor of p. And in this case, we can write p of x just like we said as q of x times x minus k for some quotient polynomial q. So in other words, if k is a 0 of this polynomial, then x minus k is a factor, which means that k is an x-intercept. Alright, so then this is why division plays a role, because it might be helpful to be able to write p of x as q of x times x minus k, and from that find our zeros. Okay, so if you think back to what we talked about with polynomial long division, we showed here that any polynomial can be written as a divisor times a quotient and a remainder. Okay, now if I'm trying to find a 0, this divisor is actually my x minus k, and the remainder hopefully is a 0. If the remainder is not a 0, then we actually haven't factored my polynomial. Okay, so that's why division comes into play. What we need to try to do is figure out if I suspect a value to be a 0 of my polynomial, let me do polynomial division, and if I don't get 0 as a remainder, then I know it's not a 0. Okay, now polynomial long division, if you remember, is a long process. It looks something like this, and it took a lot of steps. Okay, so it would be nice if we had a quicker way of doing this, and we do, and that's where we come up with synthetic division. And so I'm going to show you some examples and try to relate it back to this idea of zeros and non-zeros. Okay, so for example 1 here, I want to know is k equals -3 a 0 of this polynomial, which is this long 5th degree polynomial here. So what we want to do is try to figure out then, is x plus 3 a factor of this polynomial? I don't know how to factor 5th degree polynomials very well, so I'm going to turn to what we call synthetic division. And this is how it works. Okay, so first you're going to put your k value in a little box like this. This is the value that we're testing to see if it's a 0 or not. Okay, now across the top here, I'm going to write my coefficients of my polynomial. So that's a 3x to the 5th, 9x to the 4th, 0x cubed, 2x squared, 5x, and a -3. So again, remember, those are my coefficients. And you do need to keep up with, for example, the 0x cubed here. Alright, now from there we have a very quick process, and it goes like this. First thing you do is bring your first term down. So in this case, it's a 3. And then you say 3 times -3. So 3 times -3 gives me -9. And then I add. So 9 times -9 is 0. And then I keep going. So here I say 0 times -3 is 0. 0 plus 0 is 0. 0 times -3 again is 0. 2 plus 0 is 2. 2 times -3 is -6. I add those together. 5 minus 6 gives me a -1. -1 times -3 is +3. And -3 plus 3 equals 0. Okay, and there I have it. I have finished the division process. So what I've said is this, that p of x, this long 5th degree polynomial, can be factored like this. 3x to the 4th plus 2x minus 1 times x plus 3 plus 0, 0 being my remainder. Okay, now where did I get this stuff? So here is the 3x to the 4th, 0x cubed, 0x squared, 2x to the first power with a constant of -1. That's how I got all of this here. Okay, my k value, remember I'm testing to see if negative 3 is a value. So here I have x minus k. And that's how I got the x plus 3. And then this guy is actually my remainder. And so I had a remainder of 0. So p of x can be factored as 3x to the fourth plus 2x minus 1 times x plus 3 with no remainder here. Does that mean then that negative 3 is a 0? Yes. Does it make sense why though? Okay, so remember what we said about a 0. We said that a 0 is a thing that makes a polynomial equal 0. If I plug in negative 3 into this p function, I get 0. Now what it translated to is that means that the polynomial can be factored with x minus k being a factor. Okay, so there's my x minus k. Now, in this particular question, we're testing to see if k equals negative 3 is a 0. So how do you do that? You do division. We did synthetic division here. And since I got a remainder of 0, that means my polynomial can be written like this with a remainder of 0. It's factored with a linear factor of x plus 3. So that means that x net equals negative 3 is a 0. Let's try another one. Okay, so this time they word the question a little differently. We want to divide this cubic polynomial by x minus 2. Okay, so this is a question of division. And I should mention here that synthetic division only works when I'm dividing by a linear term. Okay, so we're having to divide by a linear term, which we are. That means I can get a k value. So in this case, my k value equals 2, right? So the way you do that is you select x minus 2 equals 0. So x equals 2. That's the value we're testing to see if it's a 0, or in other words, we're going to just divide this polynomial. Okay, so I put my k value here, 2. Across the top, I write my coefficients. That's 2x cubed, negative 8x squared, minus 23x plus 63. And we're just going to do our division here. So remember, you bring down the 2. You say 2 times 2 is 4. Then you add. So 8 plus 4 gives me, negative 8 plus 4 gives me a negative 4. Then negative 4 times 2 gives me a negative 8. Negative 23 plus a negative 8 gives me a negative 31. Now negative 31 times 2 gives me a negative 62. And when I add, I get a positive 1. Okay, so there, we've done the division. And now what this means here is that p of x equals this guy. So you drop your power by 1. That's going to be 2x squared minus 4x minus 31 times the thing I get for my k values. That's the x minus 2. But I have some remainder here, so it's plus 1. I can write this polynomial in terms of this polynomial times x minus 2 with a remainder of 1. Now as a follow-up question, is k equals 2 a 0 of p of x? And the answer to that, hopefully we can quickly see, is no, it is not. Now how do I know that? Because the remainder is not 0. The remainder is not 0, which means that this big p of x polynomial cannot be factored something times x minus 2. Now that brings up an interesting idea though. So what if you don't have a 0 as a remainder? What does that mean? Well, we can come up with something called the Remainder Theorem. And the Remainder Theorem says if the polynomial p of x is divided by x minus k, then the remainder, whatever you get the remainder to be, is the function value p of k. In other words, that means that p of x can be written as q of x, which is your quotient, times x minus k plus p of k. So whatever the remainder is actually the function value you'd get when you plug in k into the polynomial. Alright, now let me show you some examples of this, and hopefully it makes sense. Okay, so for a part here, you said, what is p of negative 3i? Okay, so we're doing complex numbers. And here we have p of x equals this 2x squared minus 3 minus 5ix plus 3 minus 9i. And we're trying to figure out what this function value is. Okay, so I'm going to do synthetic division. I'm going to write negative 3i there. Across the top, I'm going to write my coefficients. 2, negative 3 minus 5i, and 3 minus 9i. Alright, and now I'm just going to do synthetic division. It looks a little bit different because we have complex numbers here. I bring down 2. 2 times negative 3i is negative 6i. Okay, now I add. So I get a negative 3. Now that's a plus 5i. So that gives a negative I there. Now multiply negative 3i times negative 3 minus I, so you might have to do that on the side. Let's think about that real quick. So I get 9I plus 3I squared, which is going to be negative 3 plus 9I. Alright, so I'll write that there. Now I add those together, and I get a remainder of 0. Okay, so what is p of 3i then? P of negative 3i? It is 0. Alright, so that means a lot of things. That means that this thing factors the polynomial, and when I plug it in, I get a function value of 0. Alright, now quickly let's do one more. Okay, so this time we want to know what p of 2 is, where p of x equals x squared minus 6x plus 13. So I'm going to do synthetic division again, and this time I'm plugging in 2 with my coefficients being negative 1, negative 6, and 13. Okay, so I bring down the 1. 1 times 2 is 2. Negative 6 plus 2 is negative 4. Negative 4 times 2 is negative 8. And then 13 minus 8 gives me a positive 5. So the answer then, what is p of 2? 5. Okay, so this tells me several things. One, it tells me that 2 does not factor this quadratic. Okay, it also tells me that 2 is not an x-intercept of this quadratic, but also it tells me that when I plug in 2 into this polynomial, I get 5. Synthetic division is a very quick and useful tool to check function values and helps you factor. Make sure you understand the concept of a zero as well as the remainder theorem and see how these concepts interact with one another. I'd be glad to help if you have any questions. Thanks for watching.